Hello everyone, we are at the topic of BJTs and today we're going to look at BJT transfer functions. The question that we would like to answer is how would the output in the circuit change in terms of VI? The output is taken from the collector node and Vout is equal to VCE and the input is applied to the base of the BJT transistor. This is a common configuration for BJT circuits. It is called common emitter configuration, but today we want to find the transfer function for this circuit. We want to know how Vout changes for different values of Vi. We will find Vout for Vi changing between 0 to VCC. I wrote the KVL for base emitter loop and KVL for collector emitter loop here. This is VCE, IC is labeled, and this is I base. We will check for 3 modes of operation of this BJT for different values of Vi. We are going to look at for what values of Vi the BJT is going to be in cutoff, and it's going to be in active mode or it's going to be in the saturation region. Starting with the transistor operating in the cutoff mode, I'm going to write case 1 is when BJT is in cutoff. That means I base is equal to 0 and V base emitter is less than VD0. Also, I have I collector equals to 0 and I emitter equals to 0. Using the base emitter KVL and I base equal to 0, I can find the range of Vi for which the transistor is going to be in cutoff. That is Vi equals to VBE and that is less than VD0. From there, for Vi values less than VD0, the transistor is in cutoff region. Now I can use the collector emitter KVL to find the value of output, which is VCE in the circuit. I have VCC equals to RC multiplied by 0 plus Vout. From there, Vout is going to be a constant value equal to VCC. If I draw the transfer function for this circuit, I have information for drawing some part of it. So for Vi between 0 and VD0, I have Vout equals to VCC. Let's check out what happens to Vout when Vi increases from VD0 volts. Moving on to case 2. In case 2, I want to find out for what values of Vi the transistor is going to be in active mode. So when the transistor operates in the active mode, BJT is on and voltage of base emitter equals to VD0. From the base emitter KVL, I base is equal to Vi minus VBE, which is equal to VD0 divided by R base. And from the collector emitter KVL, I have VCE equals to VCC minus RC times IC. Now IC is equal to beta times IB because I'm assuming BJT operates in the active mode, and VCE is greater than or equal to VD0. Now from here I have IC equals to beta divided by R base multiplied by Vi minus VD0, and VCE equals to, from this equation, VCE equals to VCC minus beta times RC over R base multiplied by Vi minus VD0. Because VCE is greater than or equal to VD0, I can use this inequality to find the range of Vi value for which the condition of transistor operating in the active region is satisfied. With that, Vi is going to be less than or equal to VD0 plus VCC minus VD0 divided by beta times RC divided by R base. So for these Vi values, BJT is going to operate in the active region, and I can find Vout. Vout is going to be equal to VCC plus beta times R collector divided by R base. This multiplied by VD naught. Then that is, I need to subtract beta times RC over R base multiplied by VI from the first term. Now that's going to be my V out value for the given range of VI, and in this range the transistor operates in the active region. So if I increase VI beyond VD naught volts, the transistor is going to go into the active region of operation, and as long as the amplitude of VI is less than this quantity, the transistor is going to operate in the active region, and V out can be calculated from this equation. In this equation, V out is equal to a constant value minus positive coefficient multiplied by VI. V out is linearly related to VI, but the slope of the line is a negative number. Let's continue and see what happens if I increase VI and how the value of V out is going to change. Case 3 is when the transistor is in the saturation region. When BJT is in saturation, it is turned on. As a result, VBE equals to VD naught, and I collector is less than beta times I base. Also, VCE is at saturation voltage value, which we call it as VSAT. I can calculate I base from the base emitter KVL, and collector emitter voltage, I can replace it in the collector emitter KVL. So I base is equal to VI minus VBE divided by R base, and I have VCE equals to VCC minus RC times IC. From here I have IC equals to VCC minus VSAT, V saturation divided by RC. Now I'm going to use this inequality to find the range of VI for which the transistor operates in the saturation. IC is less than beta times I base. From here I have VCC minus VSAT divided by RC is less than beta divided by R base multiplied by VI minus VD naught. And that tells me that VI is greater than VD naught plus VCC minus V saturation divided by beta times RC divided by R base. For this range of VI values, the transistor is going to go into the saturation mode. VCE, or my V out, is at its minimum value, which is equal to V saturation. We are ready to draw the transfer function using the equations that we calculated. So I'm interested in the graph of V out versus VI, which is this graph. And for VI values less than VD naught, for these VI values, V out is equal to VCC, so the transistor is in cutoff. When VI increases from VD naught up until some voltage level, which is this voltage level, the transistor is going to operate in the active region. And beyond this voltage level, for these VI values, the transistor is going to operate in deep saturation mode, and V out is equal to a minimum value of V saturation. And these two numbers are not exactly equal. The reason is that for VI values between these two numbers, the transistor operates in the soft saturation mode. For our purpose, if we want to operate the transistor in the active region, which is the case when we want to use these BJTs as an amplifier, we're going to make sure that VI is less than this quantity. And when we want to use the BJTs as a switch, we want to make sure that either VI is in this range and V out is at its maximum value, or VI is in this range and V out is at its minimum value. If you look at the transfer function, this BJT operates as an inverter, meaning that when VI is at low, the output is at high value, or VCC, and when VI is greater than VI high, then V out is at low value, which for the case of this BJT, the low value of output is equal to V saturation. So it operates as an inverter. In the active region, VI and V out have a linear relationship, which is suitable for using BJTs as an amplifier, because we would like to build linear amplifiers in which output and input are linearly related to each other. We can also draw the graph of IC, collector current versus VI. And if you do that, for VI values between 0 and VD0, the BJT is in cutoff mode. As a result, IC is equal to 0. When VI increases from VD0 and the value of VI is below VHigh in this range, the transistor is going to be in the active region. I base is related to VI and I collector is equal to beta times I base. If you increase VI, I base is going to increase and IC also is going to increase. So IC has a linear relationship with I base and I base has a linear relationship with VI. As a result, IC is linearly related to VI. Now beyond VI high, the transistor will go into the saturation mode. VC is at its minimum value, which is equal to VSAT. From there, IC does not change with changing the value of I base. In other words, the transistor is going to saturate and IC is going to reach its maximum value of IC max. After that, if you increase VI, I base is going to increase, but IC is going to stay constant value. Let's see how we can use the transfer function to interpret the process of graphically finding the value of IC and VCE using the graphs that are shown on the left. The black curves are the IV characteristics of this BJT, and by changing the value of I base and VCE, the value of IC is measured and you can find it on these graphs. We have another network connected to the collector of the circuit that consists of this RC and VCE, and because of that we have a collector emitter KVL that is also called load line equation. This is called load line because we take the output from the collector and a load is going to be connected to the collector. So this equation is called the load line equation. The value of collector current and collector emitter voltage in this whole circuit must satisfy this equation, this load line equation. Also, that IC and VC must be a point on one of these IV curves for BJT. For example, for I base is equal to 20 microamp, I can have this VCE and this IC for my transistor circuit, because this IC and VCE satisfy the load line equation and they satisfy the IV curve of this BJT. Now let's look at this region, which is the cutoff region for my transistor. For VI values between 0 and VD0, the value of VCE is equal to VCC, which is 8 volts. I'm using VCC of 8 volt here. So at this point, IC is equal to 0. So this point is one of the points of this line, and also it's a point on the IV curve of this BJT. So it's a valid point. And if I look at this one for VI values between 0 and VD0, IC is equal to 0. What if I increase VI from this VD0 volts, and what's going to happen to the value of IC and VCE? I'm increasing VI from VD0 volts. So if you do that, the value of IC is going to increase. So as VI increases, the value of IC also increases. And if the value of IC goes high, the value of VCE is going to go low. So from there, it's like I'm moving in this direction on the load line. The value of VCE decreases, but the value of IC increases. So for example, if I base is equal to 10 microamp for some VI value, the value of VCE is here, and this is the value of IC for that point. Now I keep increasing the value of VI, the value of IC increases, and the value of VCE decreases. So I'm moving along this line on my load line. What happens if I reach the VI high value? what happens for VI values greater than that voltage. For VI values greater than VI high, IC is going to stay at a constant value, so IC is not going to increase, and the value of VCE is going to be at the constant value of V saturation. This is this point in here. As you can see here, the value of IC is at its maximum value and the value of VCE is at its minimum value of V saturation. The final note about BJTs is that the beta of the transistors, or the current gain of the transistor, depends on many factors. Beta is strongly dependent on temperature. As the temperature increases, beta value is also going to increase. The value of beta depends on the collector current value, so it's not going to be constant for different collector current values. In addition, beta of similarly manufactured BJTs can vary. If you look at the datasheets, usually there's going to be a range of beta value given for any transistors, as well as the average beta value for that transistor. So it's important to take note of the minimum beta value when you want to use it as a switch, because if you want to make the transistor operate in the saturation region, IC over I base must be less than the minimum beta value that you can have in this set of transistors. In summary, today we looked at the BJT transfer function for one of the commonly used BJT circuit configurations, and we saw that the output of this BJT circuit is going to be at high value when VI is at low, and for the cases of VI greater than VI high, the output is going to be at low value of V saturation. Thank you for watching.